All right, and welcome. I think we had the Symposium Economicum ask whether they could present their initiative here in the first couple of minutes of the course, and they are welcome to do so, but I can't actually see Sebastian Parada, who was announced as...
Hello, my name is Katharina. Yes, I'm from the Symposium Economicum.
Excellent.
I can just start. So let's... Can you see my screen?
Yes, we can.
Ich würde es auf Deutsch machen, wenn das...
Kein Problem.
passt.
Ja, klar.
Okay, sehr gut. Genau, also wir sind das Symposium Ökonomikum Münster, für die, die uns noch nicht kennen. Wir sind eine Studenteninitiative und wir organisieren einmal im Jahr einen Wirtschaftskongress. Der findet immer im Mai statt und genau. Der nächste Wirtschaftskongress wird am 5. Mai stattfinden unter dem Titel Envision Tomorrow, gemeinsam die Weichen neu stellen. Und dort wollen wir zusammen mit euch und unseren Referenten aus Wirtschaft, Politik, Gesellschaft, Wissenschaft, ja, unsere Zukunft aus unterschiedlichen Blickwinkeln uns angucken. Und genau, was wir machen, wir sind schon seit 34 Jahren dabei, diesen Wirtschaftskongress zu organisieren. Dieses Jahr leider digital, aufgrund der Corona-Pandemie natürlich. Und wir begrüßen bis zu 700 Teilnehmerinnen und freuen uns natürlich, wenn ihr auch teilnehmen werdet. Dieses Jahr dürfen wir 2 Hauptreferentinnen begrüßen. Einmal Simone Menne, sie ist die Multi-Aufsichtsrätin und ehemalige CFO von der Lufthansa AG. Und dann die Inka Naumann, sie ist Vorständerin bei Unilever, also 2 super interessante Frauen, die dort einen Vortrag halten werden. Und weiterhin wird es noch eine Videobotschaft von der Staatsministerin für Digitalisierung geben, von der Dorothee Bär. Weiterhin könnt ihr einen von 6 Themenkreisen wählen. Der erste beschäftigt sich mit der Arbeitswelt, schöne neue Arbeitswelt. Arbeitest du noch oder gestaltest du schon? Da soll es ein bisschen darum gehen, welche Jobs wird es überhaupt in der Zukunft geben? Welche Fähigkeiten sind gefragt? Bleiben wir beim Homeoffice oder gehen wir zurück ins Office täglich? Genau. Dann weiterhin wird es den Themenkreis Investment geben. Dort ja, geht es darum, wie Studierende auch mit wenig Geld clever und nachhaltig anlegen können und weiterhin, was überhaupt Robo-Advisors machen. Dann der dritte Themenkreis, Krisenmanagement, Challenge Accepted vom Krisen. Ein super spannendes Thema, total aktuell und ja, da soll es halt um das Krisenmanagement in den Unternehmen gehen und gerade auch im Fokus, ob Kommunikation dort eine wichtige Rolle spielt. Dann der 4. Themenkreis, Meinungsmacher, die Meinungsbildung im Wandel. Wer hat die Meinungsmacht? Genau, hier soll es ein bisschen darum gehen, wie eine Meinung überhaupt entsteht und wer die Meinung anderer beeinflusst. Dann weiterhin ein super spannender Themenkreis Supply Change. Da geht es um nachhaltige Lieferketten, Lieferketten von morgen im Vergleich zu heute, was da zukünftig noch alles passieren wird. Ebenfalls super spannendes Thema. Und zu guter Letzt Tourismus, alte Wege neu begehen, wie sich die Tourismusbranche auf die Reise in eine ungewisse Zukunft begibt. Wir merken es alle momentan, wir können nicht reisen und müssen irgendwie auf alternative Reisemöglichkeiten umdenken. Also ja, auch hier kann man, glaube ich, viel mitnehmen. Sehr, sehr spannend. Was euch erwartet, wir haben viele Vorträge, Diskussionen, aber auch Workshops, wo ihr wirklich interaktiv mit den Unternehmen und den Referentinnen kooperieren könnt. Dann wird es weiterhin noch Einzelgespräche mit den Unternehmen stattfinden. Hierfür könnt ihr euch bewerben und die Unternehmen wählen dann ja, gewisse Studierenden aus, mit denen sie gerne ein Gespräch führen würden. Falls ihr das aber gar nicht wollt, aber trotzdem irgendwie mit den Unternehmen in Kontakt treten wollt, wird es auch Q&A-Sessions geben. Das ist dann so ein bisschen wie so ein Livestream aufgebaut. Da könnt ihr Fragen stellen, mit den Unternehmen quatschen. Ja, genau. Dann wird es noch eine prall gefüllte Goodiebag natürlich geben. Wie jedes Jahr, dort findet ihr all möglichen Zeug, was ihr gut gebrauchen könnt. Und zum Abend wird es noch ein digitales Abendprogramm geben in Kooperation mit Finne und Strong Partners. Ein kleines Biertasting. Ich glaube, das wird euch auch gut gefallen. Und genau, jetzt hier nochmal alles auf einen Blick. Wir sind ein digitaler Kongress, der am 5. Mai stattfinden wird. Tickets gibt es bereits ab letzte Woche Mittwoch auf som.ms. Und genau, wir würden uns freuen, wenn ihr teilnehmt. Ich glaube, es wird echt ein cooler Tag und mal ein bisschen Abwechslung auch zu den Vorlesungen. Und ja, genau. Das war's. Ach genau, und hier noch, folgt uns gerne auf Instagram oder guckt euch die Veranstaltung nochmal auf unserer Internetseite an. Genau, wir würden uns auf jeden Fall freuen. Vielen Dank.
Ja, vielen Dank für den Vortrag. Also da kann ich auch wirklich alle nur ermuntern, sich da zu beteiligen. Das ist eine tolle Initiative. Was Sie jetzt noch gar nicht gesagt hatten, suchen Sie nicht auch Mitstreiter für die Zukunft, die mit einsteigen und selber mit organisieren?
Genau, also nach dem Symposium stellt sich immer das neue Team zusammen. Ich war selbst 3 Jahre lang immer nur Gast und habe mich dann aber dazu entschieden, Teil des Teams zu werden. Und ja, ich bereue es wirklich gar nicht und freue mich, wenn ihr da auch teilnehmen wollt. Ich sehe gerade, dass meine Kamera gar nicht an war, aber gut, jetzt ist auch zu spät. Und nee, also nehmt gerne teil und wir würden uns genauso gut freuen, wenn ihr dann auch Teil des Teams werden wollt. Wenn ihr dazu Fragen habt, kommt jederzeit auf uns zu. Also mir macht es sehr viel Spaß, auch jetzt in Corona-Zeiten ist es ganz cool, mit einem Team was auf die Beine zu stellen, ein bisschen Abwechslung auch zu haben. Und ja, ich kann es nur jedem weiterempfehlen.
Ja, kann ich auch nur unterstützen. Also gucken Sie, dass Sie sich da oder auch in einer anderen Initiative, es gibt ja noch mehr, mit einbringen und sich da engagieren. Okay, ja, vielen Dank für die Präsentation, Frau Pilz.
Dankeschön.
Ansonsten machen wir das heute so, dass Andreas die Einführung in R gibt. Ich kontrolliere so lange den Chat. Also wenn Sie Fragen haben, können Sie die im Chat stellen oder auch einfach reinfragen. Und ich übergebe jetzt an Andreas.
Okay, perfect. Thanks for the introduction and thanks for the Symposium Economicum presentation. Just go there, enjoy your time and do something outside the university, but still for your studies. So today is also like a little bit, or can be, if you want to, as a Q&A session. So I'm going to present some insights into R, not much econometric insights today, but just very basic R and Rstudio use insights. And whenever you have any questions, just please unmute yourselves and try to, or not try to, but ask the questions, and I'll try to find a very good answer to your questions. Because in the previous week, we all introduced R, we discussed the reasons why we chose R for this lecture. And then we pushed you into the cold water and let you find out how R works by yourselves, which is, of course, might introduce a barrier between you and the program that you might or might not have overcome yet. So today is thought for you to get yet another, or not another, but to get an introduction to the basic skills you might need for R and the basic computations and things you can do and program with R. So whenever you have any question, just let me know or let Mr. Trede know in the chat. And we try to find sufficient answers to your questions. I'm going to share my screen right now. So my screen should be shared. And let's start with what we are using. We're using base R, and if you we're using R and Rstudio. If you have not installed Rstudio and you're just using R, what you will get is this rather ugly looking window. This is just the console window where you can type in any R command you'd like. You can use that because it is R, but it doesn't look very well, and you cannot do too much with the bare console window itself. So what we are going to do is we use Rstudio instead of base R. Let me just make that a little smaller so I can see everything. because I need to see the headlines as well. All right, perfect. Now, this is Rstudio, and this is what Rstudio might look when you start it for the very first time, but with a little different design. And before we come to anything that we can do in R, I'll just show you the way to switch the theme of Rstudio if you'd like to do that, because normally your Rstudio is kind of whitish or gray. And if you go to Tools, Global Options, and then Appearance, you can switch to a wide variety of editor themes over there. You can just pick your favorite style. I just, for me, that is Vibrant Ink, which is a very high contrast theme, so you can directly see all the meaning of the syntax highlighting immediately. So that just being said in advance. Rstudio is an editor for your R programs. And in Rstudio, we run an R session that has an environment that stores all the variables that you can think of, all the values you create, all the data sets you load into R, everything that is important to you for your computations, for your analyses, and so on. And the environment is usually shown in the top right corner. Today, right now, it says environment is empty. Well, because we didn't create any variables yet at all. On the left-hand side, you usually see the console. So this is what the big window is right now. And additionally, you should see, or you will see in a minute, the source pane or the source panel. We can create new source files by clicking on this white button with a small green plus on the top left corner. And then we choose an R script, and then the source pane opens. And in this source pane, you can just write, as in any text editor like Word, you can write your source code, any kind of text that you want to add to the source code, and so on. And after you did that, you can store this on the hard disk. And if you come back tomorrow or in a week, you can reload the file, open the file, and have all the code as you would have in a Word document storing your seminar paper or whatever. Now, what can we do in this source pane, in the source window? Well, let's start very basic, and I think that's something that you've been doing in the last week as well, by using R just as a calculator. It's a very simple way to start. We just can create a variable, for example, the variable A in here, and we say with this little arrow, that is the smaller and the minus sign, directly put together, not with nothing in between them. And we can say that this should have the value of 4. Now, there are a couple of ways to run this line of code. One way would be to just click into the line that we want to run, and then on the run button on the top right corner. Once we do that, the line we are currently in will be executed. So we click on run. And as you can see here on the right-hand side in our environment, the value A appears, or the variable A appears, and obviously A has the value 4. Let's create another variable B that is equal to 6. And there you can see I didn't click the run button, but still that B appeared on the top right corner, because the second option is to press Control Enter in order to run any argument, any line of code. So either click on the run button or press Control Enter whenever you are in that line of code. If you want to run many lines of code at all, for example, these 2 lines, then you can also mark these 2 lines. Now, of course, if you want to run 2 lines, you cannot be in 2 lines at the same time, so you have to mark them, and then you can click on the run button, and then both lines of code will be executed jointly, one after each other, of course. Now let's use R as a calculator for the first time. We can do any arithmetic operation that you know from school and from university. So we can add numbers, subtract numbers, divide numbers, and so on. So if we compute A plus B, what we get as a result down here in the console, and every result will, unless you store it into a variable, will just be printed into the console. So down here, we see that the result of a plus b is just 10. So what we would expect, obviously. We can also compute squares. For example, the square of a plus b by putting this hat symbol right to what we want to square, and then the power we want to, then the 2 on the right hand side of the hat symbol. So this is take a plus b to the power of 2. If we do that, we get as a result, obviously, 100. We can compute square roots easily by computing by the sqrt command. And by the way, I forgot to mention that in the very beginning. I don't want you to just recode everything I do just live, try to find out that live. This session is obviously recorded, and I will put in both the video and, of course, the whole script that we're working on today into the Learn web. So you will get and receive everything that we did today after today's session. So you can then, with more time, dig deeper into it, skip the introductory parts, and then look further into what we did today. So no need to write everything with you here at the same time. We can compute the logarithm, of course, of all the variables. So the log command computes logarithms. It's a command that we might need, we will need later on if we were going to estimate elasticities. So for example, the logarithm of a times b gives us a value 3.178, and obviously the log of a plus log of b gives us the same result due to the log laws. If we can also compute e to the power of something. So let's just say that in the new variable c, that is e to the power of a. Then we get a new variable c, e to the power of 4 is then 54.6 roughly. And the new variable d is log c. And what we should expect is that this variable again is 4. And as you can see here, all the basic mathematical operations obviously work, which is very good. If we want to compare values, so for example, compare which value is larger, a or b. Of course, that's trivial for us now because we know that a is larger than b. But if we have a large data set and we want to compare which values are smaller than 10, for example, in our data, 10 is the annual income in 10,000s of euros, then we can filter out all the persons or all the individuals that have an income of smaller than 10,000. Then we can do this comparison by either comparing whether a is smaller than 5 with the smaller sign, and obviously a is 4. So this should return us a value that somehow indicates that this statement here, a smaller than 5, is true. And if we do so, we get, as a result, the statement true with all capital letters. And that is a logical variable in R. Logical variables can be either true with 4 capital letters or false with 5 capital letters. So for example, if we check whether a is larger than 5, then we would obviously get a false down here because a is 4 and thus smaller than 5. One last check, if we want to compare two values for equality, not for inequality, we can do that by the double equal sign. So if we want to check whether a is really the same as d, so the same as log of e to the power of a, so it should be the same. So let's have a look at that. And now R tells us that this is true. So these are the 3 possibilities to compare values to each other. Of course, we can also add equal signs here if we want to compare smaller or equal, and an equal sign here if we want to compare whether a value is larger or equal than some other value.
There's one question in the chat concerning the arrow, the assignment operator. So is it really necessary to use the arrow, or is it also possible just to use the equal sign?
It is possible to use the equal sign here, but I would highly recommend to not do so, because first, it's common sense in R to use the arrow. Secondly, you can distinguish between giving function arguments, we will come to that in a second, because you can only support arguments to a function with the equal sign. You cannot use the arrow there, and these classical assignments which use the arrow. So I would highly recommend to always use the arrow for assignment and the equal sign for function arguments, because then you can directly distinguish these two only by looking at them. Okay, these variables, these 4 variables are pretty useless. So A, B, C, and D, we won't need them anymore. If we want to remove them from the workspace, we can do that directly by the rm command. Rm is for remove. And if I type in rm of the object A, then our object A vanishes from the environment. So what I need to do next is to just remove all the remaining objects, and I can do so also by just typing them separated by a comma into the rm function. Let's do that again, and then we see our environment is empty again. One very important thing that we haven't discussed yet are comments. Comments are very, very helpful if you have code that is more complicated than these little trivial snippets here. So if you have code that first transforms the data in a maybe complicated way, then runs a regression, then computes confidence intervals for your estimators, then it is very handy to comment your code. You can comment, or you can add comments to your code with the hashtag symbol, and everything that comes after the hashtag will be completely ignored by the R interpreter. So every text after a hashtag is just a comment. It's for you to understand what you were doing when you were coding, creating the code. You can also use hashtags to create some sort of table of contents of your program, because if you end a comment again with 4 hashtags and click on this icon on the top right corner here of the source pane, what it opens is the table of contents of your program. And if this is a very long program, you can scroll through the chapters by just clicking on the respective link that directly brings your cursor to the beginning of that line. So you need to end a comment with 4 hashtags. You don't need to begin it with 4 hashtags. A single hashtag would suffice here, but you need to end a comment with 4 hashtags to give Rstudio the knowledge that this is a headline for your table of contents.
That's very handy. I haven't seen that before, actually. There are 2 more questions in the chat. Sure. The first one is that command that removes all the variables at once. And the second question is, there's a little broom in the environment window, at the top of the environment window. Can we use that as well?
Yeah, that's the command that erases everything. So just click on the broom and it will erase everything. So that is the easiest way. There is a command to erase everything, but I don't have it in mind right now because I always use the broom if I want to get rid of really everything. So if you want to get rid of all the stuff that you've done before, just use the broom. Include all the hidden objects if there are any, and then your environment is as good as new. Perfect. Now let's continue with the second topic of today, that is the working directory. Working directory. So, as you can see here, a second chapter has been added to the code. Now the chapter is the working directory, and we will now work on what is the working directory and how can we change it, how can we make use of its existence. The working directory is particularly important if you want to read in many data files, if you want to do that directly in your code, and if you want to have a little shortcut so you don't need to always specify the full path of the data files you're reading in. So, for example, if I wanted to read the data file bsp1.csv, by the way, this file bsp1 I added that to the Learn web, so if you want to retry what we do today yourselves, you can download the file from the Learn web. So if I want to use the read.csv command on bsp1.csv, I get an error down here. Fehler in File, kann Verbindung nicht öffnen, zusätzliche Warnmeldung. In File, Datei, kann Datei bsp1.csv nicht öffnen. No such file or directory. So this file doesn't exist. Why is that? Well, the reason is I'm currently searching for that file in the directory C uses a_masu01/documents. And in this working directory, which is the current working directory, there is no such file. The file, in fact, is here at C uses a_masu01 desktop r/intro. That's where I saved that file and not in my working directory. So I can either type in the whole path to the file, or I can change the working directory before, and then I only need to type in bsp1.csv. So let's just do that. First, before we set the working directory, I said the working directory is written down here in the console. Another way to get to know about the working directory is to just type in getwd. And as you can see here, this is the very same path as the one that's written down there. In order to set our working directory, we can use the setwd command, and then we just type in the whole directory we want to have as a working directory. That is that one. And as a result, we get nothing. If we get nothing in setwd, everything worked out fine. And as you can see here, the working directory here changed to the one I wanted to have. Now let's copy and paste that code again. Let's rerun this, and still we can't find this bsp1.csv. Well, that is because it is a comma-separated value formatted file, but it's actually a text document. So the ending is .txt instead of .csv. So let's just switch that. And another error appears. The problem here is that R, with the read.csv command, expects you to deliver data that has an exactly certain format, namely that the variables in the dataset are delimited from each other by a comma. That's what the CSV means, comma separated values. So between the columns, we have a comma. But having a look at that dataset, we see that there are 4 variables in there, variable 1, variable 2, variable 3, variable 4. But in between the variables, we have semicolons instead of commas. So we cannot use read.csv, but we would need to use read.csv2, which is usable, which can work with German data format. Now, if we use read.csv2 of this text file, we get this whole data set. We have 4 variables, and we have 100 observations. So we have 4 columns in the dataset and 100 rows. And if we only write the comment read.csv2 of BSP1, then the result of that will only be printed in the console. Might be handy if we want to see what the dataset looks directly, if we only want to read the dataset, but if we want to do any kind of computation based on that dataset, then this is pretty useless, and we need to assign the data set that's on our hard disk to an object in our working space. So let's just create an object and call that object BSP1. So because it's the BSP1 data set, we might call the object BSP1 as well. And once we did that, the object appears up here, and it is a data set. It's basically a table, but it appears up here as data in contrast to the A that we had previously, which was under the headline values. So if you have a very large environment with hundreds of variables, maybe then all the data variables appear in the data section, and all the single values or matrices or vectors appear in the values section. So if you're looking for a variable, just make sure whether you're looking for a data variable or for a value. And these are ordered alphabetically. So let's get rid of A again, now that we have that. Now this way of importing a data set is not very handy. It's a way that technically always works because it only relies on very basic R packages, those that are shipped with the standard version of R. But finding out how the data is formatted exactly is not very handy before reading in the dataset. And finding out about all the columns might be a lot of work in a larger dataset. So there is a much more comfortable way of importing datasets into R inside Rstudio, and that is using the reader package. We can do that by...
Sorry, Andreas, before we continue, there's another question in the chat. Is it also possible to write read.txt instead of read.csv2?
Let's have a look at that. Read.txt. I don't know that function because I'm never using read.csv myself as well. If you have no idea about a function, just type on the function's name, then you can press F1, and then what should open is the help to that function. I pressed F1 now a couple of times. It didn't do anything. So what we can do is we can print help for read.txt, and then it tells us read.txt doesn't exist. So probably that's a function that isn't even existent in R. If we put 2 question marks in front of it, we will get also results for packages we didn't load yet. And again, there are no results found on that function. So I guess, no, that won't be possible.
So maybe we should add that the dot is really part of the command. It's not like in Python, for instance, some kind of method or so. It's really part of the command, and read.csv2 is just one entity. So it's not read something which is a CSV file, but it's really one command, one entity.
Yeah, that's perfectly right. That's a good explanation. I didn't mention that. And now, before we go to the reader package, because we are currently at the help, if you need any help on any function, just click on the function's name, press the F1 button, and then the help function down here opens, and you can see, for example, that read.csv is just a variant of the read.table function, and the first thing you supply is the file name, and then there are many other options. And in read.csv, you also add the file name, and the separator by standard is the semicolon, and the decimal sign by default is the comma. So German data format with 1,79 as a number, also 1,79 as a number, and a semicolon to distinguish between variables. Now, I said there is a way more convenient, comfortable way to import datasets. That's by clicking on Import Dataset. And then from text and in brackets, it should say read R, reader, which is a very nice package to import datasets. And then a new window opens. You can browse through your files in order to get to where you want to get to your files. And now we want to import BSP1. Let's just do that. It takes a second to load the dataset. And as you can see here, we already have many rows, but these rows don't look very well because we only have a single column, but we know already that we have 4 variables. Well, that obviously also happened because the delimiter that we decide for down here, well, it says delimiter, is right now a comma. You can switch that to a semicolon, wait a second, and then we have a table that now contains 4 columns. So the 4 variables we are interested in, but be careful, the first variable has a data type double, so that's a floating point number, so a numeric type, that's perfectly fine. Second variable, perfectly fine as well. Third one is perfectly fine. But variable number 4 is a character, and characters are text. But obviously these are numbers. But these numbers, as we said before, are formatted in German, in the German format, 1,12, 0,23, 0,12 und so weiter. So we need to change the locale down here. So let's just configure the locale, click on configure, switch the decimal mark here to a comma and the grouping mark to a point. So if you want to write down 1000 as 1.000, you can do that with the grouping mark. Click on configure, wait another second, and then variable 4 is a double as well. And now we can do two things. The first one is we can copy that code that is generated down here to our clipboard by clicking this little button here. Then it automatically copies everything to the clipboard. And secondly, we click on the import button, and then this 5 or 6 lines of code will run. First, we load the package we need. Then we load the data set. And then we open the data viewer to have another look at BSP1. We don't need that right now. So let's uncheck that box. So this one, this view BSP1 vanishes. We can copy that again. We can import the data set. BSP1 didn't change, of course, because it was already imported correctly. And we can paste the code into our source file. And if we come back to the source file tomorrow, we can work with this code. Now, let's just save our source file with Control S. First file.r. This is then our first R file. And R files, that's a convention as well, should have the ending point R to indicate both any other user that this is an R file, and for Rstudio, it's also important to know, because if we double click on that file in our folder, because it's a .r file, it is automatically opened in Rstudio, the program we want to open it in.
And there's another question.
Yeah.
There's another button when you use the import dataset function, the base one.
Yeah.
Is that also possible?
It is possible, but by far not as beautiful and usable as the reader package, especially if you have larger data sets that, for example, contain dates and more texts and other stuff. So it is possible to use that as well. I would go with the reader package because it is the most, in my mind, the most elegant way to import data sets. Because let's have a look again. If you had data, for example, data formatted, so year, month, day variables in there, you could change that directly to a date or to a time format or to a date and time, if you also have the time of that specific date into your data set. And you can specify the exact date format, and then all the data file, all the dates will be imported as date and time format. So you could later on pretty easy work with them and have them, for example, if you want to plot a time series, have a nice x-axis to work with. Okay, that's about the reader package, or about the way to get data into R. If we have data in R, we obviously not all the time want to work with the whole data set at once, but we're interested in, before we start to run a regression, something we will learn in the next couple of weeks, we want to look at the data. We want to display the data, plot the data, add specific aspects of the data to the plots, and so on, compute summary statistics. So nothing that we actually want to do on the whole data set, but only on subsets of the data. So for example, in this BSP1, we only want to compute, for example, the mean of variable 1. Then we need to access that variable. and we can access variables of a data set with the $sign. And you can see that right here as well. We have BSP1, $variable1. That is this numeric series here. We have BSP1, $variable2, that accesses the second variable. Let's have a look at that, how that works. We can type in BSP, and if we only type in BSP, the outer completion of our Rstudio tells us, well, there is an object BSP1. This little symbol on the left-hand side tells us that this is a data object. Are you referring to BSP1? Because in this case we are. We can auto-complete this code with the tab button. Just hit tab once, and then we have BSP1 instead of just BSP. It's very convenient for longer variable names, so you just type in the first couple of characters and the rest might be done by auto-completion. And then you can type in the $sign, and our Rstudio is very comfy here as well because it shows you all the variables in the dataset. And then you can select either by clicking, or you can navigate that with the arrows. You can select one of the variables, for example, variable1. And if we run this line of code, we get all the values from this first variable. It's 100 values because we have 100 observations of 4 variables, and they are written down here. And as you can see here, we have 3 lines, and before each of these lines, we have this brackets and a number inside. So these brackets are used to access what's inside our variables. So inside variable1, we want, for example, to access the third element. So we want to extract this 11 here. So what we can do is we put the brackets behind and the 3 inside the brackets, and that would give us the third element of our variable1. So let's run this code, and we should expect that this returns 11, and it does. So let's have a little more applications of these squared brackets in order to indexing. So let's create another chapter indexing. 1, 2, 3, 4, and now you can see the third chapter is indexing. Let's, for example, let's start with indexing vectors. So we index vectors by first we create a new test vector, and vectors can be created by the concatenation command. So the command that just puts all the numbers in a row and then returns them as a vector, and that is the small c command. And a vector might be 1, 2, 4, and 3. So these 4 elements are now one object that has 4 numbers in it. You can see it here in the values section. The object is 4 elements long. The elements are 1, 2, 4, and 3. And we can access all these elements, for example, by stating test vector of 1, which gives us the 1. And we can access them all individually. Then obviously the second element is 2, the third element is 4, and the fourth element is 3. So nothing too spectacular. What we can also do, is to exclude elements from our selection by stating minus some number. If we exclude the third element of the vector, we only have 1, 2, and 3 left. So what we get is 1, 2, 3. So with a minus, we can exclude variables. With without a minus, we can select variables of a vector. We can also select multiple elements. So test vector squared brackets of another vector 1 and 3, for example, selects the first element and the third element. So 1 and 4, obviously. Now let's do something. We talked about comparisons before. We can compare test vector to larger than, whether or not test vector is larger than 2. What we expect to get as a result is a false, a true, a false, a true, and a true, because 1 is smaller, 2 is smaller, 4 is larger, 3 is larger. So let's have a look what happens. False, false, true, true, exactly what we wanted to have. we can store this logical vector in a new variable, call it larger2. It appears at the values section up here in the top right corner. And larger2 has the 4 values false, false, true, and true. And now we can also use this larger2 vector to extract all the elements of the vector that are larger than 2. So test vector at larger2 will deliver exactly those numbers that are larger than 2. Obviously, that doesn't make any sense for this test vector. But for example, if you're interested in all the class sizes in a school data set that are smaller than 20, then you have a number, then you might get 30 different numbers containing all the average class sizes that are smaller than 20. And that might also contain information you might be actually interested in. So in this dummy example, it's not important, but on a larger scale later on, working with data sets, creating first a selector vector, a vector to select elements, and then using that element on our data is a very convenient way to subset only the data we are interested in. Now that's common knowledge for us. Let's now finally work again with BSP1. We select the first variable and we want to have all the values where this variable is larger 10. Before that, we need to create a variable larger 10. That is BSP1 $variable1 larger than 10. So a variable that contains now 100 logical values. Some are true, some are false. And with BSP1 squared brackets larger 10, we select only those numbers from the data set that are actually larger than 10. Okay, this has been something on the very basics of R. Now I'd like to go a step further and have a look together with you at the California school dataset, because that's the running example that we will see all the time in this semester, because the Stock and Watson is heavily based on this kind of data set that is observational data from 1999, so already a bit older data set, but still a very interesting data set. And it's a cross-section of all the 420 school districts in California. So let's just load that data set and then work with the data set a little. So let's use the reader. Let's import CA schools. This is not the same data set that you can find in the LearnWeb. It has the same content, but it just misses some of the columns that you have in the LearnWeb dataset. So don't be confused with that your dataset will look a little different once you import the California school dataset, and because it also contains more information than my dataset does. Nevertheless, let's have a look at the dataset, and we see it is again delimited by a semicolon. So let's switch from comma to a semicolon. Wait a second. Then it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 columns. But the first column is just X1, is called X1. And it is only a running number from 1 to 420. So an index of our observations, we don't really need that. So let's click here on this little arrow and on skip, because we don't want to load that. And then we have the district as a number, we have the school as a character, the county as character, we have some information on the grades and so on and so on. But we also have CalWorks, so the fraction of people that are supported by, that get support from the state, because they don't work and don't earn money, or they only they don't earn enough money to support their children fully support their children. So they participate in the CalWorks program. But this obviously is a number, but it's written as a character 0,51. So obviously the locale is German in here again. So let's switch the decimal mark to the comma and the grouping mark to the point. click configure, wait a second, and then CalWorks is a double, and all the other variables we might be interested in are doubles as well. Let's, for now, skip the data viewer, copy this whole thing to our clipboard, click on import. Then we have our dataset CA schools, 14 observations of 420 observations of 14 variables. So let's create a chapter, the California school data set. Let's paste the code that we have that was automatically generated for us in here and have a look at the data set now. By using the viewer, we could have left this inside, of course, but I just wanted to paste the code first, show you that it has been loaded before opening the viewer. So we can type in view of CA schools and get the whole data set as in an Excel spreadsheet, for example. We can't change anything in here, but we could filter, we could add filters. We can, for example, only use certain counties. So for example, Alameda, and we would get only this single count, this data set that is with respect to this single county. So if you want to have some very first insights to your data set, you can use the viewer to do so. All right, let's get rid of that again. Because now what we are going to do is we want to work with that data set a little bit. Again, sorry, let's go back to the viewer. What we have in the data set, besides the districts and schools, so the district numbers and names and the county that they're in, is we have the number of students in the school district, so the total number of pupils in a whole district, and we have the number of full-time equivalent teachers in the district. So for example, in the Alameda County, in the Sunol Glen Unified School District, we have 10.9 full-time equivalent teachers and 195 students. 50%, 0.5 of all the students are eligible for CLWorks. So probably one of the students. 2% of all the students are eligible for either subsidized or free lunch. So whenever parents earn under a certain threshold of money, their children might become eligible for free lunch or for subsidized lunch at their schools. We have a number of computers of 67 in that school district. Remember that the data set is from 1999, so a time where computers existed but were not that frequently seen especially in schools. We have the average per student expenditure in that district. So how much does a school pay for each student? So not for the parents, obviously, but for teachers, for the building, for class materials, for sports places, and so on and so on. We have the average income of the parents in the district. We have the share of non-native speakers in the classes. So we have the fraction of those who for whom English is not the first their native language. And we have the read score and the math score. What we are interested in, especially in the Stock and Watson's examples, is the class size. So that's something that is missing here. And the second thing we're interested in is the test score. And we only have a read score and a math score. So we first need to compute the class size from the dataset. That's done for you already in the LearnWeb dataset. And secondly, we need to compute the test score. That's also done for you in the LearnWeb dataset as well. So you don't need to bother with that, but let's just do that right now because it gives us some, we can see how we can do that. Especially how to add or how to add this new column to the dataset. Now let's start with the class size. If we have 195 students at that district and we have roughly 11 or 10.9 full-time equivalent teachers, then we can just divide the number of students by the number of teachers to get something that is at least an approximate of the typical class size in that district. Obviously, every student has many teachers and every teacher has many students, teaches many classes. So this is not the exact class size in the district, but an approximation of how many students each of the teachers has. So let's first compute that, and then secondly add that to our data set. To do so, we need two things. First of all, we use this CA schools with capital CAS as a backup and create a new variable CA school that is has just the same content, just in order to have this here as a backup if we compute anything that is wrong, so we can directly go back to our first data set and we don't manipulate the original data set, but can come back to that again later. So let's now work with CA school. Let's have first a look at CA school teachers. And we see all the numbers of teachers in the districts. We already saw that 10.9 is the number of district in the first number of teachers in the first district. The number of students in the first district was 195, so all the numbers of the students. And now we only need to divide one by the other. And that's a very nice and convenient thing about R. We can directly create new variables for this data set by stating that CA school $str for student teacher ratio is equal to the number of students divided by the number of teachers. Then it computes this on the right-hand side and assigns it to this new variable inside our CA school object. Have a look at CA schools up here. It has 14 variables right now. And if I run this code, oops, that was the wrong variable. It adds a 15th variable to that. So we can just add a new variable simply as simple as that. That was the one variable that we wanted to define. The second variable is the test score. So CA school test score, for example, is then just the average of math score and reading score. So we take CA school math plus CA school read, divide that by 2 to get the average score of these two exams. And we have a 16th variable that is test score. Perfect. Now we can get a very first visual approach on our data set. We have already looked a very tiny bit into the viewer, looked at the data set. We have already seen the test scores, math and reading are somewhere between 600 and 700, for example. But if we want to have a first graphical approach, a histogram might come in very handy to get an overview of the distribution of the test score among all the school districts that we have. So we can now create histograms. So we get a first visual impression of the dataset. And using histograms. Right. Histograms, we can either, to create histograms, we can use the hist command of R, or to create a little more informative and slightly more beautiful histograms, we can use the trueHist command of the mass package, and to load a package that contains a variety of additional functions that are not included in the base packages, we can use the library command and then the name of the package. So as we did up here, or as was done automatically for us with the reader package, with library reader, we can also use the mass package for the trueHist command down here, and we can load the mass package with the library command. If you're starting R for the very first time, the mass package won't be installed on your computer. To do so, you can go to Packages, Install, then type in mass, maybe click on mass, and then make sure you have checked the Install Dependencies box here, because then all the packages that mass itself depends on will be installed as well. That might be many packages if you're installing huge packages as the tidyverse or something. It might be none, but make sure that this box is always checked. And then you would click on install, and after that, the mass package would install. I don't do that right now because I already have the mass package loaded. It would ask me to restart the R session, and because I have other R sessions open right now, I would get an error message because it cannot overwrite the mass package because I'm currently using it in other R sessions. So I'm just going to click on cancel. If you want to install it, just click on install. And then you would also get the code of how to install it down here. If you want to do that in code, then it's the install packages command. And then as a text in apostrophes here, put mass, M-A-S-S, all 4 capital letters. And that would give you the code that you could copy into your console or your script that installs the mass package. Now let's load the mass package. If you don't get any warning after the library command or any error after the library command, everything has worked out fine. You won't get a text telling you that it has loaded perfectly. Now let's come to the TrueHist command. The TrueHist command creates a histogram, and it's a histogram that has an area of 1. So it can be very useful to if you want to draw the density function of, for example, a normal distribution inside that histogram, because you are already on the same scale as a density is, because the area under it is 1. Now, we wanted to have a look, for example, at the histogram of test scores. Let's have a look at that. And then we see that the distribution of the test scores is rather symmetrical. Around 660 seems to be the mean and the median in here. We have a little more schools that are below the mean than schools that are above, but somewhere it's a rather symmetrical distribution with a rather weak flank. There is no district that is really a very bad outlier like in the 500s, and there is no district that is as good as that it would receive like 740 or 760 points. We want to get another look, for example, at the student-teacher ratio. We can just copy that, put it into the TrueHist command, and we see the student-teacher ratio seems also to be distributed relatively symmetrically, somewhere between 14 and 26. So the smallest classes we observe in the data set are slightly larger than 14, and the largest classes we observe in the data set are somewhere around 26. Another interesting distribution might be the distribution of income in the districts. And as we can see here, that is no longer symmetric at all. We have districts where the average income is below $10,000 per year and per capita. We have many districts where the average income is between 10 and 15,000 euros. We have many districts that are between 15 and 20,000 euros, but we also see a very few districts where we have incomes that exceed 40,000 and that even exceed $50,000. And that is $1999, so 22 years ago. So with inflation kicking in, that would be an even larger number in today's dollars. Back then, and additionally, this is the average income per person in the district. It's not the maximum of an individual's income, but it's an average over a school district. So you can see that the school districts, the income of the parents in the school districts is very heterogeneous between districts. And last but not least, let's have a look at the histogram at the expenditure per student. Just out of curiosity, how much does a school spend per student? And you can see here, this is far less right-tailed as the income, but still some schools tend to spend much more than the average, and some schools, although the left flank is closer to the average, spend significantly less than the average, or substantially less than the average that's of the median that is spent per student. Okay, based on this information, we might want to get additional knowledge on this data set. So for example, we might want to find out which school districts perform the poorest in the data set. So we want to identify certain districts. To do so, we have already seen in these lines up here, 45 to 60 something, we first create a variable that contains whether we want to select a certain school district now or not, and then we can select them in this fashion. So let's do that. First of all, we want to identify school districts that perform poorly in the test. School districts with poorest test performance. And let's have a look again at the test results. You can, by the way, browse through your plots down here, like a little browser in the plots window. And very handy, you can also export your plots as images. By clicking on export, then as image, choose a directory here, drag and draw the size and format of the plot up here, or type in the width and the height of the plot that you want to have. Give it a name, hist of str, click on save, and then your plot will be stored on your hard disk. A very nice and easy to use tool to store your results permanently, by the way. So now let's assess which school districts perform poorest or have the poorest test performance. And going back to the plot, to the histogram of test score, we see that, well, I would say everything below 620 is a very bad performance of the students in the test. So let's just select those schools that have a test score below 620. So let's create a variable poor test that is equal to CA school $test score being smaller than 620. Doing that will create a new vector with 420 values, many of them being false because many school districts obviously perform better, but some of them are smaller than 620. And now let's find out which ones exactly. CA school $school gives us the name of the school district. Although they might sound like schools, they are not schools, but school districts. And we only select those which perform poorly in the test. And that's these 14 school districts are those that have a test score, an average test score of below 620. What we can also find out is the school districts, the 3 school districts with the smallest class size, because we're interested later on in the effect of reducing class size on the students' performance. So it might be interesting to, first of all, have a look at those districts. Which districts are these? Which is the socioeconomic background of the persons living in the district? How is school funding done in the district? How is there additional help for the students, and so on and so on? So to first have some more information on those top 3 districts with respect to class size. So 3 school districts with smallest classes. Let's first define our threshold. So we currently don't know which is the school with the 3rd smallest class. So in order to find out, we can sort cschool.str. If we do that, we get all the values sorted. We see the smallest school has a class size of exactly 14, then 14.2, 14.5, 14.7, and so on. So, and we want to have these 3 districts, the one with 14, 14.2, and 14.5. So this one here, the 3rd element, is our threshold. We can define this as a value now. It's 14.5421 and so on. And now we select everything from the data set that is smaller or equal than where the class size is smaller or equal our threshold. So let's do that. We get a vector that again has 420 values. Let's look at that vector. And 3 of these values, this one and this one and this one, 3 values obviously are true. And now we only need to take this line of code, and instead of putting poor test into the brackets, we put small classes into the brackets, and we get the 3 school districts with the smallest average class size. So it's McLeod Union Elementary, Chicago Park Elementary, and Woodside Elementary. These 3 school districts. Now let's have one more thing that might be interesting for us. It's the wealthiest districts. And say, let's go back to the plot of income. Say that all districts above an annual income of an average annual income of 30,000 per person, these are the wealthy districts. So in this case, we know the threshold. So we can state that the threshold is 30 right now. The wealthy districts are those where CA school dollar income is larger or equal to the threshold. And then we want to select, we can, for example, select the schools in the wealthy districts. So let's run these 3 lines of code, and we see that we have 22 school districts that are very wealthy. Now we only have the names of these school districts. That might be very interesting, but doesn't help too much because we have a whole data set on these districts. So we can also look not only at the names of the districts, but at all the data that we have. And we can do that by typing in CA school. And instead of saying $school, we don't say anything there. Put in wealthy districts inside the brackets with a single distinction before to the line above. We put a comma there. CA school itself is a data set. It's a table. It has rows and columns. With this way of selecting, so a value or several values, a comma, and then several values. So for example, 1, 2, and 3, we can select all the rows where wealthy districts is true. And from all these rows, we select the columns 1, 2, and 3. So the district number, the school district's name, and the county. If we, instead of putting in 1, 2, and 3, leave this space behind the comma blank, then all the columns, all the variables of the data set will be selected. So everything that we might be interested in for these wealthy districts will be selected. So the test score, and we see already the first 10 test scores are all larger than 680. So these districts are not only wealthy districts, but obviously that they perform very well in tests as well. And that is one of the strong relationships in the data set that we will encounter frequently in this semester, is that not only class size might matter for the learning outcome, but that obviously the income of the parents also has some sort of influence on the learning outcome of the pupils. Which nature that influence is of, we can discuss in the subsequent weeks, but just mention that test score obviously seems to be somehow how related to the income. Sometimes it's a very good idea if we create a new data set if we work with a data set for the very first time, to have a look at the correlations inside the data set. So, of course, not at the causality inside the data set, that's what we want to observe in the end, but on how are variables related to each other? How is, for example, the fraction of persons that are eligible for free lunch, how might that be related to the test score? How might the student-teacher ratio be related to test score? How is income related to student-teacher ratio? So how is income related to class size? So what we can do then is we can compute the correlation matrix of our data set. Now we can only compute correlations, or at best we can compute correlations for numerical variables. So variable 1, 2, 3, and 4 in this data set are non-numerical variables, so we might need to exclude them from the computation. So we will compute the correlation matrix for the variables from students, so from the fifth variable to the 16th variable. Computing correlations in R is pretty straightforward with the correlation command. And let's create a new chapter, compute the correlation matrix of all numeric variables in CA's school. And again, creating a new chapter. So let's compute that correlation of CA school. Squared brackets, I said we want only the variables 5, the 5th until the 16th variable. We want all rows from these variables, so we leave the space before the comma blank, we select all rows, and 5 to 16, this is a shortcut, this colon here, for 5, 6, 7, 8, 9, 10, 11, until 16. So just marking this little snippet here creates this vector ranging from 5 to 16, a very nice and handy shortcut if you need to create integer sequences. Now let's have a look at the correlation of the correlation matrix. Let me make this one here slightly smaller, rerun the code so we have this in one line, and it's barely readable because we have 6 or 7 digits behind the comma. So let's just use this code, but round it to 2 digits after the comma. So we use the round command of the correlation matrix, of every element of the correlation matrix after the second, rounded to the second element. And then we have a correlation matrix. We, for example, see that there seems to be a perfect correlation between the number of students and the number of teachers in a district, which in some sort, of course, makes sense. The more students I have in the district, the more teachers I need, and the more teachers I am allowed to hire as a school. So that, in my mind, makes perfectly sense. We have different other correlations. For example, student-teacher ratio is correlated to test score with a correlation of minus 0.23. So we have a negative correlation, but a rather weak negative correlation, especially if I, for example, compare it student-teacher ratio and test score is minus 0.23, but test score, for example, and CalWorks is minus 6.3 test score, and lunch is minus 8.7. So we have a much stronger correlations between other variables than between student-teacher ratio, so class size and test score. We can also visualize this result very neatly with the core plot package, which I'm going to do right now. Very nice package. And we only need to put, once we loaded the package, a core plot. So let's load that first. We use the core plot command, which creates a plot of the correlations within the data set for us. And now we can see which are the strong positive correlations with large blue circles and the strong negative correlations with large red circles. So the larger the circle, the stronger the correlation, the bluer the circle, the more positive the correlation, the redder the circle, the more negative the correlation. So this plot gives us also a very good first impression of what the dynamics in the data set might be. A different kind of plot is obviously the scatter plot. It's a plot we are using very frequently to get bivariate plots of the data we are interested in. So in our case, we are most often interested in the dependence between or the association of student-teacher ratios or class size and test score. So we can create a plot of these two variables. The plot command in R is very versatile. It can cope either with vectors or with a matrix that contains two columns. We are using a version here that just contains works with vector, the default scatter plot function. We have an X argument, we have a Y argument, and we have lots of other arguments that we can use to customize our plot and individualize our plot to our specific needs. Let's start with a rather ugly but perfectly fine basic plot. CA school $STR, so class size is on the x-axis. And by the way, here you can see that I named the function argument. So x is equal to CA school $STR. So that tells R that on the x-axis we want to have this student-teacher ratio. You cannot use the arrow in here. You can only use the equal sign in here, coming back to one of the first questions. Always use the equal sign inside functions for naming the parameters, and always use the arrow outside of functions to assign new variables. And on the y-axis, we want to have CA school $test score. Now let's run that plot. That's the cloud of points that is created by the command. The x-axis is CA school $STR, the y-axis is $test score. And if you have a look, maybe close an eye, you can see that you have a slightly negative dependence between here. So putting a line with a negative slope through this cloud of points might be sensible here. Nevertheless, this plot is not very beautiful and not very informative, and you will please never supply such a plot to any thesis you hand in, because this plot is missing almost everything. It is missing a main title. We can add this with the main parameter. In this case, it's test score versus class size. The label descriptions are CA school $STR. Nobody can do anything with that. So let's create an X label that is class size, and a Y label with YLab that is equal to test score. Now that plot looks a little better now. We have the X's labeled in a meaningful way. We've given it a nice title. But what we could also do is we might, of course, change the color of all the points inside. So let us just change the color to dark blue. And let's change the symbol a bit to a solid point, so with PCH, and you can look that up in the help as well, equal to 20, you can get solid points now in dark blue. What these numbers in PCH mean, you can just find out yourselves later on. Just read in the help and you will find a manual of PCH, or just try to create your own plot and play around with the numbers here. So let's run this code, and it looks even a bit better. The color has changed to dark blue. You might like it, or you might not like it, but you can change colors with the col attribute here and the type of the symbol with PCH. Sometimes it is admissible to add certain points of this graph. For example, the mean of class size and the mean of test score. We would maybe want to add these averages. So let's just compute average score is the mean of CA school $test score, and the average STR is the mean, and there I used equal signs, sorry, is the mean of CA school $STR. Let's create these two variables. And then we might want to add the average test score as a horizontal line and the average class size as a vertical line. So let's have a look at that. How can we add lines to an existing plot? You can use the AB line command. AB line has two distinct ways of using it. Either you support coefficients A for the intercept and B for the slope of the straight line you want to have drawn, or you tell it to draw a horizontal line at a certain position and a vertical line at a certain position. Currently, we want to have a horizontal line at the average test score and the vertical line at the average class size. So we say that H is equal to average score. Well, let's make that color somewhat golden. Rod is a nice golden color, and give it the average STR on with a vertical line at these two lines. So we have these two lines added to the plot. What we can also do is we can make the lines a little thicker by stating the line width is equal to 2. Now we get thicker lines. So you can play around with this plot command a lot to find out which solutions suit you the best. Before we do that, before I finish for today, I'd like to come to one, I think, very interesting plot that shows, I think, a lot of what's going on into the dataset. We've seen that there is some slight negative dependence, obviously, seems to be between class size and test score. The larger the class size, the lower, at least in tendency, is the test score. If we do that same plot, not for the student-teacher ratio, but for the share of persons that are eligible for free lunch at their school, then we see a completely different picture, because we don't see a slightly negative dependence that is more or less just a tendency, but what we see here is a very strong link between, of course, the x-axis shouldn't say class size, obviously, but free lunch eligibility. So we have a very strong negative connection between the number or the share of persons in the districts who are eligible for subsidized or free lunch at school. So actually the fraction of people who can be considered poor, and the test score in the district. We will come to that topic in, I think, many of our subsequent lectures, and because obviously there's, or what we should consider, there is no causal effect. If I cut lunch subsidies, I couldn't expect test score to increase only because every student is at 0 here. So we will incorporate some of these variables that will not, or that we think don't have a causal effect in the subsequent weeks, and we'll learn how to do that and why to do that. Yeah, that's basically what I wanted to show you today in ours, so that you can now, tomorrow and on Wednesday, again, try to work on yourselves in the classes. So do you still have any questions that you'd like to have answered today? Well, that does not seem to be the case, unless someone is typing very slowly. Then thanks from my side, and I wish you a nice day, and see you next Monday, and enjoy the class tomorrow and on Wednesday.